Hello everyone, welcome to Geeks and Geeks channel. This session will introduce you an assembly language program for LPC2148 ARM7 on sum of first 10 integer numbers starting from 0 to 9. So let me give you a brief introduction how to write an assembly language program in a Keel Microvision 4 editor. Okay. So first of all, to create a project, we need to click on the project here in the menu bar and click on new Microvision project. Okay. Once you do that, it will ask you to create a project file. Okay. So you can create your own folder here. Let me create a folder here in any workspace. Okay. Create a folder here, new folder. I'll write test project. Okay. Test project, and you can give the name of that particular project. In that particular folder I'm giving the name. Okay, I will give it as test, and you can see the extension of the project file will be .uvproc. Okay, Microvision project. Save it. Once you save it, it will ask you for the selection of the microcontroller. Here you have to go for this NXP founded by Philips, and here we have to check for LPC2148 because for all the programs, we are writing an assembly language program for LPC2148 based on ARM7 cores. Okay, based on ARM7 core. So we have to select LPC2148, search for that LPC2148 here. You can find it here, and you can see the description here. It is an ARM7 TDMIS based high performance 32-bit. See, all the registers are 32-bit. Of course, the ALU, everything is 32-bit here, and it is a RISC microcontroller, reduced instruction set computer. Okay, RISC microcontroller with the thumb extension, 512 KB on chip, flash ROM with the ISP, that is in system programming and in application programming, 32 KB RAM. We have 32 kilobyte of RAM. Okay, it is a vectored interrupt control, and there are several other information which is related to LPC2148. Now once you select that LPC2148, you have to click on OK. Okay, as you can see here, I had already selected it, right? Okay, click on OK. Okay, then it will ask for this prompt: copy Philips LPC2100 startup code to project folders and add file to project. For all the software projects, you can click no. For all the hardware projects, okay, we have to click on yes. We require the startup.s project folder, but as of now I'm clicking on no. Once you do that, you can see one target folder got created here, and in that you can see also there is a source group 1. So this is the group in which we need to add up our ASM file, that is an assembly file here. Okay, now once you get this, we have to click on here file new or create an empty document here. Okay, now I'm going to write one small program for data transfer instructions. So as you can see here, I had written one small program for data transfer operations here. Okay, so once I write this program, you need to save this program. Okay, you can click here save the program and save it in the same folder in which you have created your project file, that is a test project folder, and here you can name the name of your program. Okay, I will write it as test itself, test.asm. This is an assembly program. .asm is extension for every assembly language program. Save it. So once you save it, you can see everything. There are some colors and all it has come because it indicates various types of data here. So all this these are the data hash, whatever you give, R3, R1, these are all the registers. Okay, now let me explain you this program. So this program is a very simple program to show you the demonstration of all the data transfer operations here. So you can see TTL, this is an assembler directive, and this is nothing but the name of your program, and this is the code segment area. Okay, the name of the area is proc. Okay, and this is a code segment and it is mapped to read only. This is an entry point in which we are going to write the logic of the code, right? And this is the start and stop labels, which is left justified, and the logic of the code we are writing towards the right. At least one tab space has to be given here. Okay, now, and you can see there are I am using R0, R1, R2, R3, 4 registers I am using just for the demonstration purpose. Here you can see the value of 1 is added to is moved to the R0, and you can see the hexadecimal value. Whatever the number you write with 0x, it is nothing but a hexadecimal, and when it gets stored in R1, it is showing you the 32-bit value. Okay, because all the registers in ARM7 are of 32-bit numbers. Okay, similarly, when you store the data, it is going to, what does R2 will store? R2 is not going to store 21. R2 is going to store the hexadecimal of 21, and the hexadecimal of 21 is a 15. Okay, because 16 ones are 16. What is the remainder is 5. So 1 and 5. 1 5 will be stored. So it will store it in 0x00000015. Okay, and if you want to copy the register from one data from one register to another register, you can use these operations and all. Okay, and this is to load and store the data, because only two operations is involved in the memory, that is to load and store. Load is to load the data from the memory to the register, and store is to store the data from the register to the memory. Okay, it's a simple program. However, in the future sessions, I'm going to explain you each and every single instructions. Okay, anyways, so once you write this program, you have to click on this target folder, double click on the source group 1. It will ask you for the assembly file here. Check for the files of type, select ASM file here. Okay, once you select ASM source file here, click on that particular file, test.asm, click on add. Once you click on add, close. Okay, and please verify that it has been added to the group successfully or not. That is test.asm. Once it is added, now it's time to compile the program. Okay, compile the program. Here you can translate it. You can see there are 0 errors and 0 warnings, and then you have to click on this build. Okay, once you have built the program, you have to click on debug. This is a debugging session, and when you click on this debug, click on OK here. You can see several windows. There are register windows, disassembly window, text editor window, command window, and there is a memory window also. Okay, and if you want to see the memory, you can click on here, memory 1. Okay, watch 1, UART cables and UART serial windows also, you can see it here. And to see that, you can click on view here. Okay, if the memory window is not coming, you can click on view, and you can see there are several windows, whichever you would like to have it. All the UART windows, you can see it in the serial windows. Memory windows, you can see it here, memory 1, 2, 3 and 4. Like to see the outputs and all, you can make use of these options here. Okay, and if you want to increase the font of this program, you can directly go to edit, go to configuration. Okay, in the configuration, you have to go to this colors and font, and click on this ARM editor ASM files, and click on this Korean new. Okay, and here you can increase the size of the program. Click on OK. Okay, and you can see that there is a change in the size of the font size of the program. Now to trace the program, we can just see some options here. Okay, you can see step F11 or F10. Okay, now to go for a single step line by line execution, you can see it here. You can go through here, move R0, 1, and you can see the results here. See here, look at here, R1 0x21. Okay, now you see what is the value stored in R2. It is 15. Hexadecimal of 21 is 15. R3 will store the same value as that of R1, R0. Okay, and you're loading and storing. Okay, that is going to use some of the registers. So when you use the LDR R0, R1, that means you're loading the data from the memory to the register. So you're loading the data, okay, in the which is pointed by R1. The content of that R1, content of R1 will have the data, and that data is stored in memory, that you're going to load it in a register R0. Similarly, R0 data, you can also send it back to the memory using STR, okay, instructions. So this is how we are going to debug the programs here. Fine. Okay, now let us proceed with the program. Hello everyone, welcome to my channel. In this session, we are going to write an assembly language program to find the sum of 10 integers for LPC2148 ARM7 code. Okay, so first of all, let us understand what we have to solve. So we are going to have the 10 integer numbers, that is from 0 to 9. Okay, so we have to keep on adding the first two numbers, like 0 and 1. The result is 1. Next 1 plus 2, the result is 3. Next 3 plus 4, 3 plus 3, so result is 6. In that manner, we have to keep adding until we have added up all the 10 integers. Now to perform this task, we have to write a program in assembly language. Okay, and the editor, what you can see here, it is a Keel editor Microvision 4. Okay, I'm using the version 4 here. Okay, so let us start with the program. In the first line, you can see the instruction is written as TTL sum of 10 integers. It shows that TTL is a title. So title, okay, TTL is an assembler directive. Okay, and whatever you write beside it, it will be considered as the title of the program, right? And after that, you can see there is a code segment area. Okay, the name of the code segment area is sum of num. Okay, code segment is a segment in which we write the logic of the program. Okay, the logic of the program will always be written in a code segment. That is why you can see here name of the area is sum of num. Okay, and it is a code segment and it is mapped to read only. It is mapped to only read only. Okay, now we have two labels here, symbols here, entry and end. Okay, between that we have to write the logic of the program, right? Now starting with the first label start, and you can see that all the labels are towards the left justification here. Okay, whatever instruction you write, you should give at least one tab space. Okay, and you have to write the program. This is how the program will be written. Fine, you can see all the labels are at the left. Start, next, loop, store, sum, all are at the left. Whatever the logic of the program, we are writing at least one or two tab space towards right. Okay, now next is we have written LDR R0 comma equal to sum. So before we proceed further, we should always understand that we require two registers, especially to store the first two numbers. Because we are taking the numbers from 0 to 9, we have to keep on adding it. 0 plus 1, 1. Next 1 plus 2, 3. Okay, next 3 plus 3, 6. Right? So we require two registers. Those two registers what we are taking here is R1 and R2. Remember this. Okay, because we are initialized R1 to 1 and R2 to 0. And also we required one more register which will hold the address of the memory. Okay, address of the one of the memory. I will tell you what is it. That is nothing but the sum here. In a normal C program, okay, if I want to store the final result, how do we write a program? We write int C, C equal to A plus B, right? That means the addition of A plus B will be stored in the variable C. Similarly, in this case also, we have to reserve 4 bytes of a memory location in a memory. And that is labeled as sum here. And to reserve that 4 bytes, we have to write DCD. This is called a define constant data. Whenever you write it as DCD for any particular variable, it will reserve 4 bytes of memory. 4 bytes means 32-bit. It is very clear that each and every register what you use in ARM7 are all 32-bit registers. Okay, and at a very initial stage, I am initializing the value as 0 to that because we are not started with the task here. Okay, so now to store the final result, okay, to store the final result, I need to have the address of that memory location. One should always know the address of the memory location so that he can store the data back into the memory. Okay, and to do that, I need to hold the address of that particular memory location and I will store it or preserve it in one of the register. And that register what I'm using is R0. Okay, and meanwhile, please note a point here. There are only two operations happens in a memory. That is load and store. What does load and store mean here? Load means you are going to load something. Okay, that is it can be an address or it can be a data from the memory to the register. From the memory to the register. And store is to store the data from the register to a memory. Please make a note of this point. That is why whenever we are going to operate with a memory, we are only going to use these two operations, that is load and store. Right? Now, R0 is holding the address of that label sum, or you can also call it as the address of that particular memory location to which we are going to store the final result. That is why we written equal to means address. Okay, address of this sum. Okay, and now in that memory location, what is the value stored? 0. I hope you understood this first line. Okay, now as I already mentioned you that the first value is 1, which is stored in the register R1, and the second value is 0, which is stored in the register R2. Correct? 0 and 1 we are going to take from the value 0 to 9, and we are going to check for this instruction. See, for example, we are written CMP R1 comma hash 10. Here hash represents data, equal represents address. Okay. Now, when you write the CMP R1 comma hash 10, it performs the subtraction operation. Okay. So what it does means R1 is holding the value 1. 1 minus 10 is how much? Minus 9. Okay. So why we are performing this one instruction means we need to check whether we have completed all the 10 iterations or not. Okay. Only after 10 iteration we are able to get the final result. Now to do that operation, we have to write this statement here, CMP R1 comma hash 10. Okay, now we are going to check for one branch instruction. Branch on equal, go to the label store here. Okay, now branch on equal will only satisfy when the value is 0. Now as of now R1 comma hash 10 is minus 9, and minus 9 is not equal to 0. So in that case, this instruction will fail and your pointer will go to the next instruction, that is ADC R2 comma R2 comma R1. Now whenever you look at this instruction, it looks like we are going to add these three registers here, but it's not the case in ARM7. So whenever you write R2 comma R2 comma R1, the assembler will try to add these two numbers R1 and R2, which is stored in the register R1 and R2. Okay, and store the result in this R2. Okay, that is why in ARM7 all the instructions are whatever you write the register in this particular ADC or add instruction, and when you have 3 operands here, no, it is going to be called as triadic instructions. Triadic instruction. All instructions are triadic instructions in ARM7. Okay, that's the reason it is going to sum up these two values from these two registers and store them back into the R2. And we are written ADC because ADC stands for add with carry, because from 0 to 1 we don't have carry. Now definitely when you go further, right, after we write 6 plus 4, okay, at that time there is a chance we get an carry. For that purpose we are writing ADC. Okay, and if you are checking from 0 to 3, then no need of ADC because there won't be any kind of carry. Okay, so we are written ADC R2 comma R1. So of course R1 and R2 will be added, so 0 and 1 will be added, so it will give you 1, and that 1 will be stored in R2. Right, now we have performed the first operation. Now we are going to increment the iteration by 1, and to do that we have to add that R1 by 1, and we write it in this way, add R1 comma 1. So R1 will be added with 1, R1 will become 2, and 2 will be stored back into the R1. Now I need to repeat these instructions n number of times, that is 10 times. Okay, and to do that I'm using this loop B next. So we are going to loop this set of instructions for 10 iterations until we have satisfied all the conditions. Okay, and the only way to come out of this loop is whenever the R1, whatever the value is stored in R1 is 10, because 10 minus 10 will give you 0. Then only branch on equal will satisfy, and it will help you in coming out of this loop. Till there it will keep on looping it. Okay, so of course in the next iteration definitely 1 plus 0 become 1. Now 1 plus 2 will become, so of course the value of R2 will be 3. For the next iteration it will be 3 plus 3, that is 6. After that it will be 6 plus 4, that is 0A. Remember here after 9 comes A, because we are using hexadecimal numbers here, not a decimal number. Okay, hexadecimal. In hexadecimal how the numbers will go? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0A, 0B, 0C, 0D, 0E, 0F. After 0F comes 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. After that 1A, 1B, 1C, and it goes on in that particular fashion. Okay, right? And finally once it's done with all the iteration and it is going to this particular condition will satisfy, now you jumped out of the loop and we are going to store the final register what is there in R2 in the memory which is pointed by the register R0. Okay, R0 is holding what? R0 is holding the address. Now to the address I can't write it in this way. Okay, now I need to write I need to store the data what is stored in R2 in the content of that particular register. That's the why we write it in a square bracket. We enclose that R0 in the square bracket because I need to store the data in a memory. I need to store the data in a memory which is addressed by that R0. Okay, if you give me the address, I can reach to that particular place. That is how this particular instruction works. And finally, we are going to end this instruction. So this is a very small program. Now let me tell you how we are going to execute this program. Okay. So first of all, we have to save the program, okay, in the particular path, and then we have to translate this. Okay, when you translate it, we can see that it has assembled the assembly program here, and you can see there is 0 errors and 0 warnings. After that, you have to build your program. Okay, and you can see that we have no errors and no warnings. Now we have to debug the program. Okay, start debugging the program. It will tell you this is a evaluation mode. So this editor is an evaluation mode, and it will take up to the size of 32K. Okay, click on OK here, and it will take you to the debug mode here. Now you can see there are so many windows here. So this is called as a register window, where you can see all the registers from R0, okay, R0 to R15. Total 16 registers are there here, and you can see this is the text editor, and this is a disassembly window. This is a command window, and this is a memory window. Fine. Now let us try to trace our program. To do that, we have to click here. Okay, this one, or you can press F11 in a keypad. Okay. Now this is a step-by-step instruction. Now please observe these registers here. You can see the change here. Okay. Now you can see the R0 is holding what? R0 is holding the address of that sum. Okay, address of that memory location to which you are going to store your final result. Right now. Okay, I'll go to the next step. R1 has become 1 already. You can see there R2 has become 0. Now I'm going to compare R1 and 10. Okay, 1 minus 10, it is minus 9. Of course, do you think BQ is going to work? No. Say it has skipped this label, right? It has went to the very next instruction. Now you can expect the answer now. Now what is the value of R2? What is the value of R2 as of now? 0. 0 plus 1 will give you what answer? 1. You can see here 1, right? So in the same fashion, you have to repeat. So it is repeating, right? Second iteration, now it is in the third iteration, like that. Total 10 iteration it is going to work out. Okay, so you can keep on seeing the values here. Okay, 0 plus 1 1, 1 plus 2 3, 3 plus 3 6, 6 plus 4 0, a plus 5. Okay, in that particular fashion it is going to work. Okay, a plus 5 is 0f, 0f plus 6 is in that fashion it is going to work here. 15 and 15 plus 6 is 1c. Till there we had come now. Okay, now you can expect 24, right? 1c plus 7. So you can see 24, yes, 24, 9th iteration. So one more iteration is left, and 24 plus 9, next iteration will give you 2d, right? Look at here. Yes, we are done with the 10 iterations now. Okay, we are done with the 10 iterations, and see the final answer what is there into R2, that is 2d. Yes, 0a, can you see here? 0a, R1, 0a means 10 in decimal. Okay, 0a is hexadecimal number, but if you want to convert into decimal, it is 10, right? Now we are done with all the loop instructions, and now you can see this BUQ will satisfy, and it will jump outside of this loop, and it goes to this particular label. Now it's time to store the final answer R2 into the memory location which is addressed by R0. Okay, it has done, and you can see the value 2d here. Okay, this is how we execute this assembly level program in this Keel Microvision 4 editor. Hope you all understood this particular program. Thank you so much.